Okay, so we've got a couple more chapters left. I know we only have a week, but we're not covering everything in both of these chapters. We're just doing a little bit of Redox from chapter 14 today, and then we'll do a little bit of nuclear chemistry from chapter 15 on Thursday. And then you've got your final next week. Now, the final exam schedule, one section is officially at 8 a.m. Monday, and the other section is 8 a.m. Tuesday based on the class times. But I will do the final exam similar to the other exams. I'll open it Monday morning at 8 a.m. and it'll be open all week. So it'll be open till Friday at midnight. So you have next week, anytime Monday through Friday, to do the final exam. It'll be timed like the other exams, so you've got to pick a time and have the time available to sit down and do the final. I'll send you guys more information. I'll try to throw together a condensed study guide for you. But basically, for now, you can go back and review stuff from the previous study guides. So let's get going today on oxidation reduction reactions, or redox reactions. So that's what we want to talk about now. Here we go. So a redox reaction is a reaction that involves a transfer of electrons from one reactant to another. So it's a little bit different than a typical chemical reaction. Typical chemical reactions involve breaking bonds and forming bonds. And when that happens, sometimes there's also a transfer of electrons, okay? But sometimes it's just breaking the bonds, so kind of splitting it between things and things resharing a different way. Whereas in a redox, you actually have something that initially had these electrons and gives it to something else. Okay, so it can be a little different. Sometimes it's combined also with breaking and forming bonds. But for something to be a redox reaction, there has to be something that is actually losing electrons and something that is gaining those electrons. And the reason it's called an oxidation reduction reaction is because each of those terms is related to a loss or gain of electrons. Okay, so we call it an oxidation when a substance loses electrons. Okay, and we call it a reduction when it gains electrons. And you can't have one of those without the other. Okay, so you can't just have an oxidation reaction or a reduction reaction. They have to happen in pairs, and so they have to happen together. If something loses electrons, there has to be something that's going to pick those up. Okay, and you can't have something magically gain electrons out of nowhere. So these have to happen together. Now, it's important that you know those terms and you can identify oxidation and reduction, and you can keep those things straight. So sometimes it helps people to use some mnemonics. And so you can use the mnemonic oil rig. And so that tells you oxidation is a loss of electrons and reduction is a gain of electrons. So that's one way to look at it. If that helps, great. If not, you can ignore it. There's another one that you could use instead if you'd like. Leo Gur tells you loss of electrons is oxidation and gain of electrons is reduction. Okay, and so those are just two tools that you could use to kind of help you keep these things straight. Otherwise, you just need to know what oxidation is and what reduction is. Okay, so how we identify these things is actually by changes in what we call oxidation states. So an oxidation state is kind of our tracking system for electrons. And so it's kind of, it seems like a charge. It's not a charge truly, but it, we assign different elements, say an oxidation state of 0 or an oxidation state of +1 or +2 or -1 or -2. And we do that for each element within a substance within an entire reaction. And then we look at, are there any changes in those oxidation states? And changes in oxidation states are going to indicate that you have either an oxidation or a reduction of a particular element, okay? And so first, before we can get to actually identifying oxidations and reductions, you have to be able to assign oxidation states, okay? Now, there's a set of rules for this. Now, depending on what resource you look at, they'll kind of communicate the rules a little bit differently or put them in a different order. So your book does have a table of rules that you could utilize. That will work. Otherwise, I rearrange it a little bit to an order that I think is more logical, but it's up to you. You need to be able to assign oxidation states or oxidation numbers, we use those interchangeably, to substances within a reaction, okay? So what I would say is you always look for the easiest stuff first. And so what you want to look for is, do you have anything that is a free element? And when I say free element, I mean an element all by itself, you know, and it's neutral. So it's neutral, no charge, okay? And it's not bonded to any other element. Now it could be bonded to itself, okay? And all of those things would have an oxidation state of 0. So for instance, if we have sodium, just Na, okay, that would have an oxidation state of 0, okay? Or if I have, say, O2, okay, so just O2 by itself, that would have an oxidation state of 0 because it's just oxygen by itself and neutral, okay? So it has to be an element by itself and neutral. If so, its oxidation state is 0. Next easiest thing to kind of identify and assign oxidation states to would be monatomic ions, okay? And so if we have a monatomic ion, the charge on the actual ion is the oxidation state, okay? Say, for instance, if I had, let's stick with sodium, if I have Na plus, right? That's different than just Na. Okay, if I have Na, that's neutral sodium, and so that has a 0 oxidation state. Whereas if it's Na plus or sodium ion, that would have an oxidation state of +1. Okay, whereas oxygen, that can also form an ion. That would form oxide ion, O2 minus. So if I had that in some chemical reaction, O2 minus, then its oxidation state is -2. Whereas if it's just O2, neutral oxygen, it's 0, okay? So if it already has a charge, that charge is the oxidation state, okay? For an individual atom, okay? If you have a cluster of atoms that has a charge, meaning a polyatomic ion, it's a little more complicated because you have to break it down and you're assigning oxidation states for each individual atom, okay? So these are your two simplest cases. Now, also, when we write oxidation states, they really are written with a sign and then a number, whereas the charges are written with number and then sign. So notice like O2 minus, I wrote 2 minus for the charge, the number first, whereas when I wrote the oxidation state, I wrote -2, so the sign first. It's kind of a nitpicky thing, but you know, when you're doing the homework, if it asks you to assign oxidation states, if you type it in the wrong order, sometimes it'll tell you it's wrong and to rearrange it. So just keep that in mind. There is a proper way to write it. So those are kind of your two easiest things to assign. Next, what's helpful to know for assigning oxidation states is that if you have a compound and that compound has a metal, the metals always have a positive oxidation state. Now, when I say positive, it could be a +1, it could be a +2, a +3, and so on, okay? But it is positive, not negative, okay? And specifically, if you have a group 1 metal, you know, in the first column of the periodic table, Whenever any of those are in a compound, they're always +1. And if you have a group 2 metal, whenever they're in a compound, they're always +2. Okay, so first column of the periodic table and second column, those have constant charges when they form an ion, so their oxidation states are also constant. Okay, but for any other metal, if you need to determine the oxidation state, you want to determine what ion it is, what cation is it in this compound, okay? And that'll tell you the oxidation state because they'll be the same, okay? So it'll depend on what anion it's attached to. So if you're trying to assign oxidation states to an ionic compound, it's always helpful to just first split it into a cation and anion. That will help because that will directly give at least some of the oxidation states, okay? Next up, when we're dealing with compounds, there are some nonmetals that have some pretty regular oxidation states. So if you have fluorine and it's in a compound, that should be -1, okay? So if you had fluorine by itself, just F2, because that's one of our diatomics, it would be 0, okay? But any other time, fluorine is going to be -1, okay? So that one's an easy constant. You know, when you see fluorine, if it's not by itself in neutral, it has to be -1. A couple others that are pretty reliable. If you have hydrogen, hydrogen can be either by itself in neutral, so 0, or when it's in a compound, what I have listed here, it can be +1 or -1, and that depends on what it is actually attached to. Okay, if there's any other nonmetal in the compound, then it's +1. Okay, but if hydrogen's bonded to a metal and only a metal, well, we already know metals have to be positive. So in that case, the hydrogen would have to be -1 instead of being positive. Okay, next up is oxygen. Generally, you should assume if oxygen is in a compound that it's -2, okay? There are some cases where that's not true. If it's bonded with fluorine, fluorine can force oxygen to be positive, since fluorine has to be -1, or when it's in a peroxide type compound, which we won't really deal with, okay? So you don't have to worry about it. So for the most part, unless if oxygen's bonded to fluorine, you should assume it's -2 in a compound. Okay, next up, everything else, basically you have to kind of determine based on what everything else in the compound is, okay? And knowing the charge on the compound or on the polyatomic ion, okay? So your oxidation states within a substance have to sum to the overall charge. So if it's neutral, they're going to sum to 0. If it is a polyatomic ion, so it has an overall charge, it's all going to sum to that charge. Okay. So that's, you know, the rest of the elements, how you determine them, if you haven't determined it from things above. Okay. So if you follow this list, this kind of gives you a starting place. And if you go from the top to the bottom, it's going to make your life the easiest. Okay. If you try to jump around, sometimes you'll mess yourself up. Okay. So if you work your way down as you're trying to assign oxidation states, it'll make your life the easiest. So we're going to go through and do some examples. I have several examples already posted with the lecture slides, but I'll go through some as well. So here I've got a long list of different substances, and I want to know the oxidation states of each atom in each of these substances. Okay, so this first one, we have lithium. So that is a free element, an element by itself in neutral. And so this has an oxidation state of 0, okay, because it's by itself in neutral. Next up, we have nitrogen, N2. That also is an element by itself in neutral. So that must have an oxidation state of 0, okay? And really that oxidation state, that applies to each of those nitrogen atoms. So there's 2 nitrogen atoms in that compound, right? And each one has an oxidation state of 0. Okay, so what I'm indicating is the value for each of those atoms. Okay, and then we have the phosphide ion, P3 minus. So that's a monatomic ion. So the charge tells you the oxidation state. So if it's 3 minus ion, it must be a -3 oxidation state. So that phosphorus has a -3 oxidation state. Okay, so those first three should have been relatively easy, right? But the rest of these, we have to kind of start with the thing we know, and if we're left with anything we don't know, we narrow it down based on the overall charge. So NO3 minus, nitrate ion. Well, oxygen, I told you should assume is -2 when it's in some sort of compound, right? It's in a polyatomic ion, which is a charged compound, okay? So the oxygens have a -2 charge, but you have to be careful. That applies to all three of those oxygens. You still would say the oxygen has a -2 oxidation state. You don't, multiply it. But when you're trying to figure out what's left, you do need to consider how many you have. So my nitrogen has some unknown oxidation state, and I have 3 oxygens, and each of those has a -2. And that needs to overall sum to -1. Okay, so you can kind of set this up like an equation, right? So some value that I'm looking for, x, plus 3 times -2, because that's those 3 oxygens, that sum needs to equal -1 because that's the overall charge. So that would be x minus 6 equals -1. And so that would be x equals +5 if I add the 6 over, okay? And so my nitrogen here must be +5. Oops, there we go. And now you don't have to write out that equation to figure that out, but if it helps you, do that, okay? Now this next one, I've got calcium fluoride, so the F I know has to be -1, right, in a compound. And then calcium, if you look at the periodic table, that's a group 2 metal, so that has to be +2, okay? So that one I didn't need to fall back on that the sum needs to be 0. But in this case, it still sums to 0 because that's neutral, because you have a +2 and you have 2 -1s, right? And that equals 0. Okay, next one I have CuCl. Now, this one can seem like, okay, well, we weren't given any information about either of these, right? Because copper, well, that's a metal, so I know it's got to be positive something, but it's not a group 1 or group 2. And then I have chlorine, and that one we weren't told anything about. So then you need to think about, okay, this is an ionic compound. And remember I said it can be helpful if you have an ionic compound to break it up into its ions. So this is made up of Cu and Cl, and Cl has a -1 charge, meaning that Cu, since it's 1-to-1, must be Cu plus. So this is copper 1 chloride, and those monatomic ions that make this up determine the oxidation states of those elements. And so this chlorine must be a -1, and the copper must be a +1. Okay. And if we go to the next compound, we have the same kind of problem. We have copper and sulfur. And the rules don't tell you anything directly about those other than copper's a metal, so it has to be some sort of positive. So again, you need to be able to break that ionic compound down into its ions. This is something you should have been able to do since back in, chapter 3, something like that. So it splits up into Cu and S, and you should know, based on where sulfur is in the periodic table, that when it's an ion, it's a 2-. And if it combined 1-to-1 with copper, this must be Cu2 plus. So those monatomic ions that make up that ionic compound give us the oxidation states. So it's a +2 for the copper and a -2 for the sulfur. Okay. Okay. Next up, we've got Mg3PO42. So the oxygen has got to be -2, right? That's what we should start with there. But then we've got magnesium and phosphorus. That magnesium, if you look at the periodic table, that's group 2. So that must be a +2, okay? And then we're left to figure out the phosphorus. So this is another one that, if you remember, well, this is a neutral compound, right? And so if we sum all of these up, it needs to be 0. But you need to take into account each of those magnesiums is +2. Each of those oxygens is -2. And so you're going to sum all of that up. So we have 3 magnesiums. Each one is a +2. And that added to, well, you have 2 phosphorus because there's 2 phosphate. So 2 times some unknown value plus you have actually 8 total oxygens because there are 2 phosphates, 2 PO4s. So there's 8 of those oxygens, and each of those is a -2. And that all needs to sum to 0 because that's a neutral compound. So we have 6 for our magnesium plus the 2x. So we don't know what each phosphorus is. And then we would have -16 equals 0. So then if I add over the 16, I would have 16 on the right, and then I'd subtract 6. So that tells me 2x must be 10, okay, based on that. And then that means x has got to be equal to 5. And so my phosphorus here is +5, okay? And you can do some of this stuff in your head after you have done a few, you know, and so that's fine. But if you need to, you sit down and write these equations and figure it out, okay? Now, next one, we have the NH4-2S, okay? And so with this, well, I know that hydrogen, when hydrogen is with any other nonmetals, it has to be +1. Right? But then I have a problem because I have nitrogen and sulfur, and I wasn't told anything about either one of those. So what you need to realize is that is an ionic compound. So you can break it into its ions to help you. So if you break that into its ions, it's NH4 plus and S2 minus. Okay, so those are the ions that make that up. So the S2 minus part, that is a monatomic ion. So that tells me that the sulfur must be -2, okay? And so then I can figure out the nitrogen by knowing overall this has to be 0. So I've run out of space on the bottom, so we're going to go up here. And we're going to say, okay, we have 2 nitrogens, right? Because it's NH4-2, and we don't know what the nitrogen is. So 2x plus, well, I have 8 hydrogens because there's 2 NH4s. I have 8 hydrogens, and each one is +1. And then I have sulfur, which is -2. Okay, and that all needs to sum to 0 because that's a neutral compound. So I have 2x plus 8 minus 2 must be equal to 0. So 2x should be equal to, well, if I subtract the 8 over, I have -8, and then I add 2, so I have -6. 2x equals -6, so in this case, x must be -3. Okay, so I'd have a -3 here for my nitrogen. Okay. Okay. So hopefully you're kind of getting the idea here. And so this other set, I'll probably go a little bit quicker on. So next one, I've got HI. So hydrogen is with a nonmetal, so it's got to be +1. And then you can narrow down what I is based on that it needs to sum to 0 because this is neutral. So +1 would combine with -1 because there's just one of each of those to give you 0. And then next up, I have SRH2. And so you can start with either. You could say, okay, strontium is group 2, so that has to be +2. And hydrogen is with a metal, so it needs to be -1. And when you look at that, that's a neutral compound. It has to sum to 0, and it does because you have +2 and you have 2 -1s, and so that adds to 0, okay? But notice, as I'm writing these, I write what each individual thing is. That is very important. You can't say that the hydrogen is -2. In total, its contribution for the compound is -2, but each individual hydrogen is what we want to know, okay? Each individual atom. So now this next one, H2CO3. I have hydrogen and there's non-metals, so it has to be +1. And then I have oxygen, and so I would assume that's -2. And so then again, this one, I could say, well, I have 2 times +1 for the hydrogen, and then I have some X for carbon, and I have 3 times -2 for my oxygen, and that needs to sum to 0. And so I have 2 plus X minus 6 equals 0. So you add the 6 over, subtract the 2, and so you get X equals 4. So my carbon here must be +4. Next one, I have N2O4. The oxygen should be -2. And so I have 2 of something that I don't know, the nitrogen, okay, plus 4 times my -2. 4 times -2 for oxygen, and that needs to sum to 0. So I have 2x must be equal to 8, right? Because 4 times -2 is -8, and I add that over. And so x must be 4 in this case. So here it's +4. Okay. And then I have H2O2. Okay. Now this one might be a little confusing one because if you start out and you say, okay, well, H is with a nonmetal, so I say it's +1, and then oxygen, I'd say it's -2. But if you check that, this, if you say 2 times +1 plus 2 times -2 equals 0, well, you'd have 2 minus 4 equals 0, which is not equal, right? And so we have a problem. So this is where, remember, hydrogen in a compound is ±1. And so we're good putting a +1 there because it is with a nonmetal. But oxygen, remember, most of the time is -2. In this case, it's actually not -2. And so we can figure it out. We can say 2x here. Okay, so 2x. And then this equals 0, so 2 plus 2x equals 0. 2x would equal -2, so x needs to be -1 in this case, okay? So this is one of the oddballs, and that's because this is a peroxide, okay? And then the next one, you've got OF2. So again, be careful with that oxygen because it's with fluorine, and fluorine has to be -1. So you can write the equation, or you can start thinking about this stuff in your head a little bit. You've got 2 -1s, so that's a total of -2, and you need to add something to that to make it 0. So it's going to have to be a +2 in this case to make that sum equal 0. Okay, so that's another kind of oddball when oxygen's with fluorine. Okay, just a few more. We've got ClO2. And so oxygen, I'm going to say, is -2. And if I have 2 -2s, that's a total of -4. And so I need to add something to -4 to make it 0. So it's going to have to be +4 for this ClO2. Okay, for the Cl part. Okay, next one, I have PCl5. This one's a really weird one. This is one I typically wouldn't give you. It's a little more challenging because none of our rules help here, okay? Other than it needs to sum to 0, okay? So I wouldn't give you this like on a test or anything, but I figured I'd point out just a couple, trickier ones. So we've got PCl5. I didn't tell you anything about phosphorus. I didn't tell you anything about chlorine, because you typically don't want to start with those because they can have different oxidation states. You know, they're not always the same. But if you run into a case like that, when you have a halogen, if there's nothing else in the compound forcing the halogen to have some different oxidation state, then the halogen, like chlorine, is going to have a -1. Okay. And so in this case, it would be -1, and there's 5 of them. And so we'd need a total of +5 to cancel that out. Okay. So that one's kind of an oddball one. That was a mean. Next one, we've got pH 3. So I have hydrogen with a non-metal. So hydrogen should be +1 with a non-metal. So if I have 3 of those, then I have +3 total. I need a -3 from my phosphorus. Okay. Okay, guys, so that was a lot. Hopefully that helps. Like I said, there's more examples on the slides that you can go and look at. But you've got to be able to use those rules and assign oxidation states. But remember, you can just use the rules. You don't have to memorize them. You can keep that list, so when you're asked for oxidation states, you can utilize that, okay? But you have to be able to utilize it to assign oxidation states. Now, let's get back to then redox reactions. So once you have your oxidation states, then what you should see is in a redox reaction, there's a change in oxidation states from reactants to products, okay, for a given element. And there's going to be 2 of them changing, okay? So what you should see is on the reactant side, you have some element that has a given oxidation state. And then on the product side, that same element has a different oxidation state. And you should see that for 2 things, okay? And so one of them, the oxidation state should be going up. And the other one, the oxidation state should be going down, okay? And whichever one has an oxidation state that is going up or increasing, it's actually an oxidation, because that thing is losing electrons. And when something loses electrons, it becomes more positive, okay? Because it's losing negatives. Whereas when you see something that oxidation state's going down, that's indicating to you that that particular element is being reduced. And that's because that element is gaining electrons. If it gains electrons, it's gaining negatives. And so it becomes more negative, or the oxidation state goes down, okay? So when we look at redox reactions, that's one way we can kind of look at it. We can assign the oxidation states, and we can communicate that this substance or this element is oxidized and this element is reduced. That's one way to talk about a redox reaction. Unfortunately, there is another way to look at it and another way to talk about it, which sometimes causes a little confusion. But you have to be familiar with it, because depending on who you would be talking to will determine which preference they have, and you've got to be able to communicate either way. Okay, so you've got to understand how to identify something's oxidized or reduced. But another way to look at it is in terms of what we call an oxidizing agent and reducing agent. Okay, so this is kind of flip-flopped. It's looking at it from a different perspective. And so what we're looking at when we say oxidizing agent is we're looking at what substance allowed an oxidation to occur. So if an oxidation is a loss of electrons, the only way something can lose electrons is if there's something else there to pick them up, okay? And so that other thing that's there to pick up those electrons would be the oxidizing agent, okay? Or other terms, oxidant, oxidizer, those are all the same thing. So what you would be looking for is what substance contains the element that is actually gaining the electrons. And that is the substance that is called the oxidizing agent, okay? Whereas the reducing agent is the thing that is allowing a reduction to occur, okay? And if a reduction is a gain of electrons, then you have to have something that's giving those okay? And so the reducing agent is the thing that is giving up the electrons so that something else can be reduced, okay? So I know it can be a little confusing, but both sets of terms are so common. It's really important that you understand the difference and you can apply those terms properly. So let's look at some reactions. Now, these reactions, they're redox reactions, and I want you to identify what's oxidized, what's reduced, and what's the oxidizing agent, and what's the reducing agent. Now, when we identify what's oxidized and reduced, that is only the thing that is changing oxidation state, so the element, okay? Whereas the oxidizing agent and reducing agent, when we talk about that, that's actually a complete reactant, okay? So it can't be one of the products. That's one kind of freebie, okay? When you are identifying oxidizing agents and reducing agents, definitely do not give the answer that it's a product. It can't be, okay? But to identify all of these things, you need to assign oxidation states, okay? So unless if you're told oxidation states, which you rarely are, you have to be able to assign those first. So we'll go through these reactions, assign oxidation states. So we have hydrogen, it's by itself and neutral, so it's 0. We have iodine, it's by itself and neutral, so it's 0. And then we have Hi, hydrogens with a non-metal, so it's +1, meaning the iodine is going to have to be -1 to make that total 0. Okay, so then what I would do is look on the left side of the reaction, we have hydrogen, right? And go to the right side of the reaction and find the hydrogen and look at, did anything change? Well, yes, it went from 0 to +1. Okay, so it increased. So that's an oxidation. Okay, whereas the iodine went from 0 to -1. Okay, 0 to -1, and that it decreased, right? It went down, and so that's a reduction. So now that I've labeled all of that stuff, it should make things a little bit easier to identify, okay? So the element that is oxidized is the element that starts with a low oxidation state and increases. And so in this case, that is hydrogen, okay? So hydrogen is the thing that is oxidized. And then the thing that is reduced, in this case, is the thing that starts at an oxidation state that then decreases, and that would be the iodine, okay? And then if we want to look at it from the other direction, if we want to talk about the oxidizing agent, that's the thing that allows the oxidation, which is a loss of electrons. And so it is the thing that is then going to pick up those electrons. So it's actually the reactant that contains the reduced substance. So in this case, it would be the I2, okay? And so then the reducing agent is the thing that allows the reduction to occur, okay? And so it is the substance, the reactant that contains the thing that is oxidized, okay? Because the thing that is oxidized is actually giving up those electrons. And so the H2 is the reducing agent because it gives up electrons, okay? Okay, now we go to the next one. Let me change my pen since I'm going to be overlapping a little bit almost. Okay, so we've got sodium by itself and neutral, so that's 0. And then in H2O, we have +1 for H because it's with a non-metal, and -2 for oxygen, and that does all sum to 0 because you have 2 +1s and 1 -2. And then next, I've got sodium as a group 1, so it has to be +1 in a compound. Hydrogen, it's with at least 1 non-metal, so it's +1. And then oxygen should be -2, and that all sums to 0. So that's good. And then we have hydrogen by itself and neutral, so that's 0. And so then I look for any changes. So sodium starts at 0 and it goes to +1, okay? So I have 0 to +1 for my oxidation states. So it increases, so that is my oxidation, okay? And then I have hydrogen. It starts at +1 If you go over to NaOH, it stays +1, so that's not a change. But if you go over to the H2, then it goes from +1 to 0, okay? And so in that case, that is a reduction. Okay, so we have to have an oxidation and a reduction. Sometimes you can run into a more complicated reaction where you have multiple oxidations or multiple reductions, and so you might have 3 different changes. We'll stick to simple stuff where it's one of each, okay? So that means that what is oxidized in this case must be my sodium, because that's the thing, the oxidation state is increasing. And then what's reduced, which I guess I should be careful here, what's reduced is the hydrogen. Okay, so the H, that's what's undergoing that change in oxidation state. So it's just the H, not the H2O. Okay, because the oxygen's not changing oxidation state. So when you talk about what's oxidized and reduced, you focus on the thing that's changing oxidation state. And then if we want to talk about oxidizing, oh goodness, this pen is not working today. Oxidizing agent, then that must be the substance that contains what was reduced. So that in this case would be the H2O. So that is the entire reactant. Okay. And the reducing agent then would be the thing that's allowing the reduction to occur. Okay. And that would be, in this case, the sodium. Okay. Okay. So that's that. Now we can do a couple more. Okay. So now I've got fluorine, which is by itself a neutral. So oxidation state of 0. And then sodium hydroxide, I have +1 for sodium because it's group 1, +1 for hydrogen because it's with at least one nonmetal, and -2 for my oxygen. And I have OF2, so remember fluorine should be -1. In this case, that forces the oxygen to be a +2 if you go through and make sure that sums to 0. And then I have +1 for sodium because it's group 1 in a compound, -1 fluorine because it's in a compound. And then I have +1 for hydrogen because it's with a nonmetal, and -2 for oxygen because this is a pretty standard compound. Okay, then we look for changes. So in this case, I have fluorine going from 0 to -1. And actually, I can even connect it to this other one, right? And so it goes into 2 places, but that doesn't matter. It's a 0 to -1 change. And so that is going down, so that's a reduction, okay? And then let's see, what else is changing here? Anything? Negative, oh, there we go. Oxygen, it's going from -2 to +2. Okay, so remember, there always has to be, at least 2 changes occurring. Okay, so we have this increase, so that's our oxidation. Okay, so what's oxidized must be my oxygen in this case, and what's reduced must be my fluorine. Okay, and then the oxidizing agent in this case is the actual reactant that allows that oxidation. So it's the one that contains what's reduced. So that's F2. Okay? And the reducing agent is the one that allows the reduction. So the thing that contains what's oxidized. So the NaOH. Okay. Okay. Last one. Let's see. SiCl4. This is another mean one. I don't tell you anything about silicon or chlorine, but remember, if you're kind of at a loss and you have a halogen, the halogen's going to prefer to be -1 unless if something causes it to be different. So we'll go with that. And then we have +4 for the silicon. Magnesium by itself would be 0. Magnesium in a compound's +2 because it's a group 2. And the chlorine would then have to be -1 to make that total to 0. And the silicon would be 0. So my changes, I have a +4 going to a 0. So that's a reduction for my silicon. And then I've got a 0 to a +2 for the magnesium. So that is an oxidation. So my oxidized substance must be magnesium, okay, for my oxidized element. And then my reduced element must be silicon. And then the oxidizing agent must be what is allowing this particular process, the magnesium, to be oxidized. So that's the other reactant. So silicon chloride, or silicon tetrachloride. And then the reducing agents, what's allowing the reduction to occur. So it's the reactant that has the oxidized element. So that is the magnesium. Okay. Okay, guys. So that is, assigning oxidation states and identifying what is, happening in these reactions. Now let's look at a few more reactions, but look at this a little bit differently. So here's a set of reactions, and I say determine whether each of the following reactions are redox reactions. So this time I'm not telling you it's a redox reaction. I want you to tell me, is it a redox reaction? So how you do this is you have to remember that a redox reaction has to involve an oxidation and reduction. It has to involve some transfer of electrons, okay? And how you identify if that's happening is, again, assigning oxidation states. So if you're trying to determine if a reaction is redox or not, what you should do is assign oxidation states to everything. And then look and see, are there changes, okay? And if there's no changes in oxidation states, it's not a redox reaction. If there are changes in oxidation states, then yes, it is an oxidation reduction reaction, okay? So we'll go through and assign oxidation states. We have magnesium by itself in neutral, it's 0. Chromium, 3+ ion, so chromium 3 ion. And so it's a +3 because it's a monatomic ion, so the charge is the oxidation state. Same with magnesium ion. It's a monatomic ion, the charge is the oxidation state, okay? And then chromium 2 ion, again, monatomic ion, the charge is the oxidation state. So you'd look, magnesium goes from 0 to +2, right? And chromium goes from +3 to +2. So yes, this is a redox reaction, okay? So this one is, because you have changes. And so really your magnesium is getting oxidized and your chromium is getting reduced in this case. Okay, next one. We have sodium by itself in neutral, so it's 0. We have H2O, so you have +1 for hydrogen with non-metal and -2 for oxygen. And so that sums to 0. And then we have +1 for sodium in a compound because it's group 1. +1 for hydrogen because it's with at least one non-metal. And then what's left over for oxygen is -2, which is what we would typically expect anyway. And then we have hydrogen by itself in neutral, so it is 0. Okay, so you look and see, do you have changes? Oh, yes, you do. You have sodium being oxidized, and then you have hydrogen being reduced, right? So this one also is a redox reaction, okay? And then next one, let's see, lithium's a group 1, so in a compound it's +1. Hydrogen with at least one non-metal has to be +1. Oxygen we would assume is -2, so then we have to figure out what's left over for that carbon. So you have 3 -2s, that's -6. And you have 2 positive 1s, okay? So you need 4 more positives, okay? So the carbon in this case would be +4. I know that's getting a little tight there, but that should all sum into 0, okay? If you're considering each individual atom. Then we have Li2CO3. Again, lithium in a compound must be +1 because it's a group 1. I have -2 for my oxygen. So now if I sum all of that up to figure out what carbon would be, I have 3 -2s, so -6, and then +2 from my lithium. And so again, my carbon, I'm going to need +4 from. Okay. And then water, I have +1 and -2. That one we've done a lot of times. Then we have CO2. And so I'd assume -2 for oxygen. That's a total of -4. So my carbon's going to have to be +4. So if you look on the reactant side and the product side, what you should see is lithium's always +1, hydrogen's always +1, carbon's always +4, oxygen's always -2. So this is not a redox reaction, okay? Because you don't have an oxidation and reduction occurring. And then let's see, next up, we've got H2O2. This is one of those tricky ones. Again, that's a peroxide. And so we have +1 for H2, which actually causes our oxygen to be -1. So this is one of the compounds we did earlier. And then water we've done lots of times. That's +1 and -2. And then oxygen by itself in neutral is 0. So you can look for changes, and what you should see is oxygen. This one's a little different than the ones we've looked at. You have oxygen going from -1 to -2, but you also have oxygen going from -1 to 0. So in this case, your oxygen is actually being oxidized and reduced, okay, which is possible, okay? So there are changes. There's 2 different changes in oxidation and reduction. And so this is also a redox reaction. So it's just a little more complicated, I guess, than the others we looked at. Okay, so you guys should be able to assign oxidation states, determine what's oxidized, what's reduced, what's your oxidizing agent, what's your reducing agent, and even determine, is this a redox reaction or not, using oxidation states, okay? Now, let's move on to where redox reactions are used, okay? And before we get, into the actual application, it is good for you to know kind of one other term, and that's whether something is spontaneous or not. So when we use the term spontaneous, whether it's with respect to a redox reaction or any other reaction, remember that this is something that occurs on its own without outside intervention, okay? So I think we used this term before when we were talking about reactions a little bit, but basically if we classify something as spontaneous, this is a reaction that all that needs to happen is you put those things together and it reacts, okay? Whereas you can have other reactions that we call non-spontaneous, and those are things that we can force a reaction to happen, but we need to do something. And so it may involve needing to heat something up. It may involve applying some electricity, some voltage to it, whatever. It just depends on the reaction, okay? But for redox reactions, if we're talking about a spontaneous one, of course, this is something all you need to do is put the reactants together and it happens. So an example of a spontaneous redox reaction is corrosion. And your book talks a little more about corrosion because this is a pretty important type of spontaneous redox reaction. Okay, and when we use that term corrosion, that's essentially what we're talking about when we say something rusts. Okay, so rusting of something. And so that is actually the spontaneous oxidation of a metal, okay? And so generally, we don't want that to happen, right? And so it's good to have an understanding of redox reactions because there's ways to prevent it, okay? Now, a lot of times a redox reaction is going to release energy. If you just do a redox reaction just in one vessel, a lot of times that energy that's released is actually in the form of heat. So combustion reactions, those are actually redox reactions, okay? A combustion reaction, when you burn something in oxygen, And combustion reactions release a lot of energy, okay? And it's in the form of heat. And so that's an example. But we can perform these spontaneous redox reactions in different types of setups where we can harness that energy. Instead of losing it as heat, we can harness it in different ways. Okay, and that's what we want to talk about a little bit. But before we get to that, let's talk about just kind of a really common type of spontaneous redox reaction that's kind of easy to look at and predict whether or not it would be spontaneous. Okay. So we looked at this actually back in chapter 5. So this is almost a review of one particular type of reaction. Okay, so I already said that combustion reactions are redox reactions, right? Those are spontaneous redox reactions. But also single replacement reactions are a type of redox reaction always. And what we're going to look at, again, just review, is when we have a single replacement of a metal, okay? And so remember, we used this activity series. So this is the same activity series we had back in chapter 5, okay? To help us understand, will a metal replace another metal in a compound, okay? And so when we talked about this before, remember that this activity series is listed in order of the most active to least active, okay? Now, it doesn't have every metal from the periodic table, but it has the ones that we're looking at, okay? So if something is higher up on that activity series, then that is capable of replacing anything lower down in a compound, okay? So what happens is you start with that more active metal and it's neutral. And what happens is it'll kick another metal out of the compound. And in that process, it becomes oxidized, so it loses electrons. Whereas the less active one that gets booted out of the compound needs to actually pick up electrons. And so it picks up electrons and becomes reduced, okay? So in some examples, okay, in case you don't really remember single replacement reactions, which this is a good review because you need to go back and review things for the final, right? So here's some examples of single replacement reactions of metals, okay? And so when you look through these reactions, what you should notice is a pattern. These are all single replacement. You have some metal by itself, and you have some ionic compound that it is reacting with, okay? So potassium in the first one is our metal, and nickel 2 bromide is our ionic compound. And what happens is the potassium kicks out the nickel, okay, to form potassium bromide, and then nickel becomes nickel solid, okay? So in this case, the potassium gets oxidized and the nickel gets reduced. And then you can look through these others. You've got magnesium and then aluminum chloride, and the magnesium kicks out the aluminum. So the aluminum goes by itself, the magnesium bonds with the chlorine, okay, and so on. So these are all, examples of single replacement of metals, okay, and they're all redox reactions. You could go through and assign oxidation states and identify what's being oxidized, what's being reduced. But these aren't all actually spontaneous reactions. What you can do to determine, is this a spontaneous reaction, something that would happen on its own? You would need to look at the activity series, okay? And so we can compare each one of these to the activity series and determine, is it spontaneous or not? So you'd look for potassium and nickel, right? So we have potassium here, and we have nickel down here, right? And so potassium's higher up, meaning it is more active, meaning yes, it can kick the nickel out of the compound, okay? And so that first one is spontaneous because potassium is more active than nickel, okay? We can go to this next one. You have magnesium and you have aluminum. So if you look, there's magnesium, okay? And right below it is aluminum. So In this case, magnesium, yes, is more active than aluminum. So that also is a spontaneous reaction, okay? We go down to the next one, we have cobalt and we have zinc. So we find where cobalt is, here's cobalt, and then here's zinc, okay? And in this one, notice the way it's written, cobalt is trying to replace zinc, but cobalt is lower in the list. And so cobalt actually is less active. So this reaction, as it's written, is non-spontaneous because cobalt is less active, okay? Now, it doesn't mean that you can't perform that reaction. It's just you have to help that reaction happen, okay? It can still happen. It just isn't going to happen on its own. So those first two, you can put those reactants together in the same vessel and they'll just react, okay? But that third one, you put cobalt in with some zinc iodide in solution, nothing's going to happen unless if you then cause that to happen. You have to actually apply a voltage to it, okay, which we'll talk about in a minute. Then the last one, we've got copper and we have sodium. And so you find here's copper and then way up here is sodium. And so that one also is non-spontaneous because copper is less active than sodium. Okay, so it's lower down in the list. So it can't replace that sodium. Okay, so that really is a review from some chapter 5 stuff. And so that's just a really common type of redox reaction that is utilized. But it's not the only type. So remember, combustion reactions are also redox, and there's a lot of other forms that we've already looked at. The way you determine is something redox is by assigning those oxidation states and identifying are there changes, okay? But if we want to utilize a redox reaction to get energy, okay, or say we want to force one of these non-spontaneous reactions to happen, then we have to apply energy, okay? How we do this typically is by setting up an electrochemical cell. And so we'll look at two types of electrochemical cells, okay? So we have voltaic cells, that's one type. The other one's electrolytic, okay? But first we're going to start with voltaic cells. So a voltaic cell can also be called a battery, okay? So this is a setup that allows us to harness the energy that is released by a spontaneous redox reaction, okay? And so we harness that energy in the form of electricity when we set up a voltaic cell or a battery, okay? So within a battery, you actually have a redox reaction occurring, okay? That's where that energy or that electricity is coming from, okay? So up in the upper right corner, I've got, one of their diagrams that shows you kind of an experimental type setup. So you can go in the lab and take two beakers, and connect them by a wire and connect them by a salt bridge and set up a voltaic cell, okay? But when you have a battery, this is all done for you. So the actual part of a battery that creates the electricity, it is actually a voltaic cell. Now, another term we can use for a voltaic cell is also galvanic cell. Those are interchangeable, so they're just synonyms. But within a voltaic cell or a battery, what you have is the reactants of your redox reaction, but they're separated, okay? Because we don't want that reaction to just go and the energy to be gone because we're not ready to collect it yet, okay? So what we do is we put them in two compartments, whether it's two beakers or some other setup. Somehow those reactants are separated into what we would call half cells, okay? And one half cell has whatever needs to be oxidized, and another half cell has what needs to be reduced, okay? And so your oxidation half cell, your reduction half cell. And then how we get the reaction to occur is we connect those by a wire, okay? And so we connect them by a wire, and that wire is going to be connected to some metal piece that is put in each of those half cells. And that piece of metal that is placed inside of each of those are called electrodes, okay? And the electrode within each cell is going to allow either electrons to flow out of the cell or into the cell. And the wire connects those. And so the electrons can flow into the anode, into the wire, and then into the cathode, okay? And so that's what is actually going to happen, is that the anode's going to essentially pick up electrons from the oxidation half cell, where electrons are being lost, and it's going to carry them then to the cathode, where electrons then get dropped off in the reduction half cell, allowing this other substance to be reduced, okay? So once that wire's connected, electrons can flow. If the wire's disconnected, electrons can't flow and the reaction can't happen. And so that's how we control whether or not the reaction is going, okay? So that will allow us then, that flow of electrons through the wire, we can harness the energy from that flow of electrons, okay? So that's what a voltaic cell or a battery does. Now, in all of this, you do have to be careful. You got these two compartments, and you can't just have a bunch of electrons flowing from one to the other, because the one compartment would build up a lot of positive charge because it's losing all these electrons, and the other one would build up a bunch of negative charge, okay? And that's not favorable. So what would happen is those electrons just wouldn't flow because it would be building up all these charges. So another part of this is there's always some sort of salt bridge, okay? And so there's another connection between those cells that is filled with some ionic compound, to where then the ions of that ionic compound can flow to each cell to help balance out the charges that are caused by that flow of electrons, okay? And so that's the whole purpose of then that salt bridge. It's just to help keep each half cell neutral, even though there's electrons flowing, okay? So it can be a little bit complicated, but it's good to have just a general understanding of how is it that we can use a redox reaction to actually get electricity. And the key is kind of separating what is being oxidized and reduced and kind of limiting that electron flow, and then making it flow through the location where then you're harnessing that energy, okay? And so that's how, you know, batteries work. So when a battery is just sitting out, nothing's happening. But when you put a battery into a device, that device is connecting to each of the ends of the battery, which is creating that wire connection where the electrons can flow, okay? And they're flowing where then it allows that device to work, okay? Now, the opposite of a voltaic cell or a battery would be an electrolytic cell, okay? So an electrolytic cell is used to actually perform non-spontaneous redox reactions, okay? So remember, some reactants you can put together and they just react, okay? And if you separate those, you know, and set it up right, you can harness that energy of that spontaneous reaction by setting up a voltaic cell. But if we want to force some reaction that on its own wouldn't happen, we could set up a similar type of setup, but it would be called an electrolytic cell. The difference would be we would need to actually apply a voltage. So we would apply some electricity to force the reaction to go in the direction it doesn't want to go, okay? So we can set it up just like that diagram on the previous slide. The difference would be is just that wire, somewhere on that connection, you would have to apply a voltage. And so you'd essentially need to connect a battery to it, or, you know, you'd be plugging that device in to pass electricity through there. And if it's at the right voltage, then it's going to essentially reverse that reaction in the non-spontaneous direction, okay? So you can have a similar setup. You can have an oxidation half cell, reduction half cell. So you have that stuff separated, and you have, your electrodes in each where the electrons are going to flow. And you can have, a salt bridge to keep that charge balanced, okay? This is what happens when you recharge batteries, okay? So say you have your cell phone, it's got a battery in it. So as you use your cell phone, really you have an active voltaic cell, okay? You have a voltaic cell running, okay, when you have your cell phone powered on, okay? But when you go plug your cell phone into the wall, okay, or put it on your wireless charger, whatever you do, that actually reverses that reaction, okay? And so it applies a voltage to that cell and causes it to go in the non-spontaneous direction, meaning it regenerates all of those reactants for the spontaneous reaction, okay? And then you unplug it and then it starts working again, right? Of course, as it's plugged in, it's working and charging, but we don't need to worry about that. So we can set it up. It can be an exact reversal of your voltaic cell. Or it could be set up like the diagram is in your book. They show it as it's all one container, because those substances, they can float around in the same container and they're not going to react until you apply this electricity, until you apply a voltage to it, okay? The problem with that is if you do set it all up like that, as you apply that voltage, you're creating products for this reaction, but it would be reactants for a spontaneous one. So you would have to be extracting those as it goes if you set it up this way. So it can be a little more complicated to do that. But kind of the key is you need to be familiar with these basic terms that, when we utilize redox reactions, when we actually utilize them to get electricity or we force them using electricity, that all has to do with what we call electrochemical cells. And you can have ones that are set up for a spontaneous reaction, and that would be a voltaic cell or a battery. And you can have ones that are set up to run a non-spontaneous reaction, and that would be your electrolytic cells, okay? These are really important things that are used in everyday life. It's just when you use them in everyday life, you typically don't talk about any of this terminology, right? You just call it a battery and you're recharging your battery, right? But this all is tied to chemistry. It's all tied to redox reactions. That's why it works. And understanding it can help understand how we can create one or make a better battery, things like that, okay? Now, your book does talk a little bit more about corrosion, because that's another really important redox application that I've already kind of mentioned. So yeah, the two top kind of applications would be using redox reactions to get electricity, so making batteries. But another really important thing that we want to learn how to control or be able to control is corrosion. And so that's something in everyday life that, happens. Your vehicle rusts, right? But we don't want it to rust. And so if you have an understanding of redox reactions, you can understand how that can be prevented. Okay, so when some metal rusts, it's a spontaneous redox reaction occurring. Okay, and it happens because you have water on this exposed metal surface. Okay, and so what happens is then the metal gets oxidized, and so it forms really a more stable form of the metal. But for some metals, that is not good because it tends to be kind of a weaker physically form, and for a car, you don't want your metal surface to rust and, start to break apart. Okay. So with this, it's a little bit different than a typical electrochemical cell, so different than a voltaic cell in that the actual metal surface acts as both the anode and cathode. It's really all together, it's your half cells. So there's no separation of things. It's just all there together. And since it's not separated, you can't really control if it happens, right? Because if all the stuff is there, it just reacts. Okay. So there are methods to be able to prevent it. Okay. And so typically, like on vehicles, they coat them with paint, right? And then some nice little clear coat. But there are other ways. And so there's ways that you can connect a more active metal to a less active. So you can kind of sacrifice one metal for the other. Okay. Or you can plate some metals in others. So sometimes some metals aren't very reactive. And so you can put a thin coating of that, but the metal on the underside is maybe the stronger metal that you want those properties. Okay. So redox can be a really important concept to understand. It's really important in everyday life. Maybe not in the medical field, right? That you may not really realize. But it is, you know. So batteries, of course, power lots of stuff. So that's one reason you should be kind of interested and understand a little bit about redox. Okay, so that's all we're doing in that chapter, guys. We won't go into like balancing redox reactions and stuff. We skipped those sections. You don't need to know how to do that stuff, okay? But realize you've got to finish up. It's just a short assignment on redox reactions. If you haven't done that yet, you got to get that done today. And then you've got a quiz that you'll need to do by tomorrow night, okay? And then be ready to talk about nuclear chem on Thursday. Have a great day, guys. See you on Thursday.